presentation will be on interface characterization of sulfated zirconia supported on multi-walled carbon nanotubes, and his co-authors are Changchun Liu, Sungchun Li, Dong Su, and Lisa Pfefferle. And I apologize for the pronunciation, but we get it right. Please help me welcome Professor Howard.
Thank you. I first want to also offer my thanks or my congratulations, I mean, then the thanks to Burt for his award as Energy Fuels Distinguished Researcher in proton chemistry. The thanks is for what he's doing right now, and Bruce has also mentioned that this morning, that he's been recording our history hour, being the Catalysis, his community. And but the other thing I want to say is that he's served behind the scenes, particularly in our Catalysis Society, for literally decades. I was for a long time Foreign Secretary, Vice President, and President, and all I can say is that Burt was there when I came, and Burt was there when I left. So for that, I'm very pleased to offer my congratulations and thanks. So the topic that I have this afternoon is in fact one that he's contributed to. I guess he has all the ones that we've talked about. Early on, after sulfated zirconia was discovered and became one of the bandwagons on which many of our colleagues jumped, he had started to work on it. I looked and found that about a decade ago he stopped publishing on sulfated zirconia, but he was there for a decade or more working on it. So what's changed that we might look at it again? Well, we're searching for solid acid catalysts that will work in aqueous media. So this is a possible solution to that. It won't work probably unless you can put it in a hydrophobic environment, and carbon tube support suggests that that's not possible. From the point of view of looking at the chemistry on using X-ray absorption spectroscopy, what it advises you is you can isolate small particles of the order of 1 to 3 nanometers, and therefore you can bring to bear this spectroscopy that can probe from individual atoms and look at it from the sulfur, the oxygen, the zirconium sides, and maybe say something about what is going on that acid side on zirconium, and that's what I want to talk about today. So this is a cartoon on how we make these materials. The support is Muli-walled carbon nanotube tubes, which are functionalized by oxidative nitric acid. We then graft a zirconium precursor, that's Catalysis, onto those functional groups, and then that is annealed at 450 for 2 hours to crystallize the zirconium oxide. We can put in a little oxygen, but we can't use the traditional calcination because we burn up the tubes. And then we impregnate with ammonium sulfate and repeat this annealing at 450, and that's the catalyst that I'm going to be talking about. But I won't say any more about the preparation itself. Now, there's several reviews in the literature of sulfated zirconia, and there are, I don't know the exact number, but perhaps as many as 30 pictures of what the sulfated zirconia sites might look like. Here's one of them. And one of the things that I want to talk about is the charge transfer that we can see as we look at the zirconium edge or the oxygen edge and the sulfur edge. And with respect to the sulfur edge, try to convince you that there really are two species, a sulfate species, and then whatever the second species is that is actually the catalyst. And so what is that, and how does it share electrons? I guess it's a sub-title for me. So we have been working on the problem for some time. There are 2 recent papers that have been published, and I just want to quickly review kind of the background of just the support, which is the zirconia oxide nanoparticles on carbon tubes on which the sulfate is going to be put. So the first thing is that the zirconia nanocrystals are tetrahedral in structure. This is something that Burt looked at, the fact that sulfate will stabilize the tetrahedral structure. How do we know it's tetrahedral? High resolution TM, which there's a single particle there. Here's a blow up of that single particle, and here's a model of it. And it can, if there's a fast Fourier transform that indexes as the tetrahedral structure,
if we look at it by ordinary X-ray diffraction, we can also identify that the phase is tetrahedral zirconia. So that we know about it, which is not different than the bulk. The next thing I want to say is that we are going to focus our attention on weight loadings around 15% because only in that range do we have thermal stable small particles in the range of 2 nanometers. That means stable up to about 750. Higher loadings, you get a larger particle initially, and they are unstable towards thermal centering. And here we're going to look at them by pure analysis of X-ray diffraction. This is too small for you to truly read, but with 15% weight loading, they start out at 2 nanometers, and after being heated to 750, they remain that. At about 40-some weight percent, they're more like 3 nanometers, and after 750, they're up to about 10 nanometers. So that's summarized as stable, which you can read at 450, 650, stable at 50 weight percent, and unstable towards centering for 40 weight percent. Or you can also see it in TEM. At 450, the temperature at which they've been synthesized, the particle size is not different at the loadings, but after we center at 750, which is just barely on, there you'll see that the small loadings or low loadings stay more or less constant, but the large loadings give us larger particles. So both by TEM and X-ray diffraction, we show that they're unstable. By using small angle scattering, we can show that we have a distribution of two, a bimodal distribution. At low loadings, it's a single distribution, and then in situ, we're able to go from the synthesis temperature up to 550 and show that they're stable. But at high loadings, you have this bimodal distribution of something down here in the order of a couple of nanometers and something that's closer to 10 nanometers. And even with a modest increase of centering from 450 to 550, the smaller particles are stable, but the large ones continue to center. So, for that reason, we want to have particles which we have reasonably are covalently bonded to carbon, and they're stable thermally, and I'll show at the end that they're also hydrothermally stable, because that will be a property we will need if we're going to use it for biomass processing, but so that we're going to use that for all the remaining discussion, that loading. So here is a whole bunch of electron transfer, which has been used in X-ray spectroscopy. I'm not going to go through this at the moment, that's kind of the summary, but we're going to go and tune to the X-ray K edge of zirconia, the L3 edge of zirconia, the K edge of sulfur, and in all cases zanes, no XAF, and also we're going to do NEXAS on the K edge of oxygen to try to deduce this flow of electrons from the different atoms in the structure, where I'm representing it simplistically. It's carbon on the carbon 2 bonded to zirconium to oxygen, and then sulfur also being bonded to oxygen to zirconium. So here is the veins at the K edge of zirconia, and there are several references here. The foil, which is not very useful. The other two is the precursor, the zirconium acetyl acetate, which has the highest white line intensity, the zirconium dioxide, which has got the lowest of the oxides, and then in between them is our actual catalyst. So how do we interpret the change in intensity of the white line? So I'm doing this in detail. Similar arguments would apply for the other X-ray absorption, but I won't do them in such detail as I do here. So the argument goes that the intensity of that white line is determined by the density of empty states at the Fermi level. And so that if you have more empty states, you get higher intensity, as you do with the precursor, the acetyl acetate, or if you get a lower intensity, that means that there's more electron density and less holes near the Fermi level. And our catalyst falls right between the precursor and bulk zirconium oxide. So all I can do is do a qualitative discussion about which way electrons go. In this case, it's with respect to the bulk. With respect to the bulk, this would indicate that when we small particles bonded to carbon, that there's been electron transfer away from the zirconia. And so that's how we come to this charge transfer conclusion, with charge transfer from zirconia to the carbon nanotubes through the oxygen. Now, as I say, I'm going to repeat that argument, but not in this detail as we go to these other techniques. So I'm going to remind you a little bit about near-edge X-ray absorption spectroscopy. This is soft X-rays, windowless X-ray absorption spectroscopy. The absorption is in the same way as it is for doing the higher energy ones, but the difference is that you're exciting, let's do it from here, you're exciting, I guess it's actually here, we're exciting something from the core to a bound molecular orbital, not the continuum, as we do with most X-ray absorption spectroscopy. And once excited, we have this electron excited into an empty orbital, and the orbitals I'm going to be using for carbon-carbon, carbon-oxygen, all of the cases I'm interested here, will be an empty pi star between oxygen and some other atom. And once excited, it can decay either by fluorescence or by Auger process, but light elements almost exclusively de-excite by Auger process. And we're going to detect the electron. That makes it quite surface sensitive within 2 or 3 nanometers of the surface. But I want to make 2 statements about it. Up here, about the intensity. The intensity is determined by the density of empty states very much as the white line, but now the density of empty states in this vacant pi star orbital, and that's true whether it's involved in bonding to carbon or zirconia or sulfur. But the edge intensity, the edge binding energy shift is determined by changes in electron density of the core here. In other words, the more positive charge I put on the core, the more I drag this to lower energy. And so if there's a shift in energy, meaning that this energy is greater, that would mean that this levelized at higher energy. Okay, so that just reminds you of how XF is different from other X-ray absorption spectroscopy, and how we're looking at 2 examples. These are oxygen K-edge absorptions. They're kind of dense, 2 kinds of spectra here, but I just want to draw your attention to 2 things. Over here we have the leading edge, which is at lower binding energy, is for functionalized carbon nanotubes or functionalized carbon nanotubes which have been reduced by ethanol at high temperature in the liquid phase. And they are lower binding energy than when we have zirconia, which is shifted up. Here we've got the same situation where we've got a functionalized carbon nanotube, and then again one that's been reduced to ethanol, and there's relative to zirconia, which now has, carbon nanotubes have zirconia on it, there's a shift. So in both cases, we see a change in edge, and with respect to the intensity, we can see the case where sulfur is involved, which is it's this peak here. Underlying it is the zirconia, look at the blue case, and then this is the functionalized carbon nanotubes with no zirconia, and if we reduce them in ethanol, that intensity comes down. It's normalized, the edge jumps, so this is the average intensity on the oxygen per atom. So from that, I can draw this conclusion. The shift up the edge on graphene is real, and it's consistent with zirconia having transferred charge to the carbon nanotubes. The oxygen temperature increase, the reaction